Okay, so in this video, let's understand what the curse of dimensionality is and how it affects the performance of models. So I'll try and cover this topic from three different aspects. So the first one is, so let's take, for example, we have an ML model where we have three features, F1, F2, and F3. And also for the sake of simplicity, let's assume that these three features can only take two values, 0 or 1. So basically they're binary features, right? So look, if I want a model to perform well on my features, right? I want the data points or the features to be spread all over the entire feature space. So I want points over the entire feature space, not just at one corner of it. How do I get points over the entire feature space if I have data points with every combination of F1, F2, F3 possible? So there'll be, if you use simple permutation and combinations, there are three possible combinations, right? And so the total number of data points you can have for the three combinations is 8. So basically what I'm saying is if you have three features and they're only binary features where they take just 0 or 1 as values, you need at least 8 data points where the features 8 data points will and you will be minimum required to encapsulate or the entire variation in features so that the features or the data points are spread across the entire feature space. Now let's just assume that instead of three features we have 10. We have F1, F2 all the way to F10, right? So the total number of features required here is 2 power 10. Sorry, the total number of data points required here is 2 power 10 to, encapsulate the entire feature space, which will be 1024. So you see what's happening here. As the dimensionality increases, the number of data points we need to encapsulate the variability in our features increase exponentially, correct? So I'll just write down here. As dimensionality increases, the number of data points to perform good classification data points to perform good classification increases exponentially. So the curse of dimensionality is a real problem in classification problems. It's not so much of a problem in regression problems, but it's a big problem in classification problems. So this is basically called the Hughes phenomena. All right. What is the Hughes phenomena? Let's say I have 10K data points. Let's say I have 10K features, 10,000 features, and the size of my data set is limited in the sense that I have only n data points. The data points don't increase. Okay. Now the size of the data set is fixed. Size of data set is fixed. Okay. So what Hughes phenomena says is that the performance of the model will decrease as dimensionality increases because the space of points or the number of points increase exponentially, right? The number of points need to increase exponentially to encapsulate the entire change in the feature space. Encapsulate the change in the feature space. Okay, so this is one aspect of looking at curse of dimensionality. The second aspect basically says that, the thing is, we look at it from the perspective of distance measures, okay? Distance measures are like Euclidean distance or Manhattan distance or whatever. So The intuition of distances in 3D is not valid for higher dimensions, especially for Euclidean distance. Okay, the intuition of distances in 3D is not valid, especially in higher dimensions. Okay, basically, what this means is that what this says is, as your dimensionality increases, as the dimensions in your data set increase, the points in higher dimensional spaces start becoming equidistant from each other. Okay, the points in high dimensions start becoming equidistant from each other. Equidistant from each other. So techniques like KNN that rely only on, that rely heavily on distance measures like Euclidean distance, these techniques start to fail in higher dimensions. Okay, so in higher dimensions, KNN starts to fail. Now, the mathematical proof for the fact that, as dimensions increase, the Euclidean distance becomes equidistant, or points start becoming equidistant from each other in the Euclidean space. The derivation for that is, I'm not going to cover it in this video, but if you want to see the derivation, I'll cover it in another video. Just put it down in the comments. And the third aspect for this is also pretty simple. The third aspect is that as dimensions increase, this the increase in dimensions leads to overfitting. Okay, so when that happens, the model just starts to break down. The models don't do very well when you have models that overfit on data. When you have models that overfit on data, so as the dimensions increase, that leads to overfitting. Okay, so these are three aspects or arguments to the curse of dimensionality. I've only covered the theory, I haven't done the mathematical derivation. But if you want to see that, just leave it in the comments. And I'll make a video on it sometime later.